In this next section in 9.3, we're going to start by talking about a series 1 over n squared. And if you go ahead and evaluate it, plugging in 1, you'll get 1 over 1 squared, which is 1. Then plugging in 2, you'll get 1 over 2 squared, which is 1/4. Then 1 over 3 squared, which is 1/9. Then 1 over 4 squared, which is 1/16. And we could try to come up with a formula for the partial sum so that we could take the limit, but unfortunately, there's no good formula for this, so we'd have to use a different approach. So the question is, what do we do when we can't use the partial sums? Well, we're going to use what's called the integral test, which is what we're going to go over next. The integral test requires, though, that our function, which will turn our series into a function, or a sequence into a function, needs to be positive, continuous, and decreasing, meaning going down on the interval from 1 to infinity. And the reason why it's 1 to infinity is because that's the way our sums are. They start at 1 and go off to infinity. And by decreasing, remember, that means our function has to be going down. It means each term has to be smaller as we go from left to right. Pretty much, you could have 1 or 2 pieces that are not doing that, but overall that should be the pattern, is that it's continuous, it's a positive function, and it is decreasing. And then we'll let, like I said, our sequence, a sub n, be our function. And we'll use n just because our sequence had n's in it. And what we'll do is we'll try to figure out whether or not it's convergent or divergent. If the function, if we take its integral from 1 to infinity, notice it's infinity just because, like, the sum is infinity on top. If that integral is convergent, then the sum will be convergent. However, the reverse is also true. If that integral, that infinite integral, is divergent, then the sum will also be divergent. So this actually tells us perfect. It's going to tell us when it converges, when it diverges, based on taking the integral from 1 to infinity of, we're going to say, our function, but it's our sequence that we're taking the integral of. We're just calling it a function, just to make our lives easier. What we've noticed a lot in these recent sections is that we are treating our sequences as functions. Normally sequences are just a bunch of dots, but we're just basically playing connect the dots and looking at the full function instead of just the sequence. It's a lot easier. And we can use different properties this way. So let's take a look at this first example. In this first example, we have that we're asked to determine if the series is convergent or divergent. And we've got the series, or the sum, from 1 to infinity of 1 over n squared plus 1. And so, again, partial sums won't help us on this one. So let's see if this integral test does. So the first thing that they want us to do is treat the sequence, not the full series, just the sequence, just the items, like a function. So let's go ahead and let f of x, a function, equal our 1 over, instead of n squared, we'll use x squared plus 1, but it's still the same thing. And where x is greater than or equal to 1, because and we're doing this because our values on our sum went from 1 to infinity. So if we just switch out the n's to x's, we still need to make sure that we know that x is going to be greater than or equal to 1. Now we need to make sure that the hypotheses from the integral test actually hold. They wanted 3 things. If you go back up to the integral test, we wanted a 1, make sure it's positive, 2, make sure it's continuous, and 3, make sure it is decreasing for any value 1 or bigger. So let's see. First, is it continuous? Is our function that we just created continuous? And as long as the denominator x squared plus 1 doesn't equal 0, It is. And that is true. The x squared plus 1 doesn't equal 0. There's no value that will actually make that equal to 0. That's a real number. We know that x squared plus 1 doesn't equal 0. So it is a continuous function. On the interval that we were looking for, which is 1 to infinity. Actually, it's continuous from negative infinity to infinity, but we don't need that much. We just need 1 to infinity. 2, the second thing that we're looking for is the function positive. And by positive, we just mean positive or negative values. Let's take a look at our function. Our function, as a reminder, is 1 over x squared plus 1. So the first thing that we see in our function is we've got an x squared term. When you square any value, it's going to be positive because it's squared. Adding 1 to a positive number is still going to be positive. So if you add 1 to a positive, it's still positive. So adding 1 is still positive. And also there's a 1 on top, which is positive. So at the very end of the day, the whole thing is going to be a positive divided by another positive value, which is going to end up being a positive value. So is this function f of x positive? Absolutely, yes. And just like our function was continuous, now the third thing we needed to check, and you don't need to check these in the same order as long as you check all three, is our function decreasing? Is f decreasing? Remember, we learned in calculus that the quickest way to find out if a function was increasing or decreasing was to take its derivative. So let's take the derivative. If it's positive, remember, what does a positive derivative mean? Then the function is increasing. If it is negative, then the function is decreasing, going down. Remember, the derivative gives you the slope of the graph, the slope of the tangent line. Remember, slope positive means going up, slope negative means it's going down. So you have to think of derivative means slope. So let's take our derivative. So we've got our original function, f of x equals our 1 over x squared plus 1, and we want to take its derivative. So we're looking for f prime of x. And there's a couple of ways to do this. I think the easiest way would be to rewrite the 1 over x squared plus 1 as an exponent. We'll rewrite it as an x squared plus 1 to the negative first power, because when we bring up this piece, we would write it to the first power, but when we bring it up, it makes it the negative first power. And technically, yes, there's a hidden 1 out in front, but you don't need to rewrite that. It can be hidden. And then if we actually take the derivative of it this way, we are using chain rule instead of quotient. If you leave it on the bottom, you have to use quotient rule. It's just a matter of fact as to whether or not, which way is easier for you. Chain rule says to take the derivative of the outside part part first, which is that -1, which means bring down the power. Decrease the power by 1, so subtracting 1 will give you actually -2. Leaving the inside the same, which would be x squared plus 1. Then the last part of chain rule says to take the derivative of the inside part, the x squared plus 1, and multiply by that. Well, the derivative of x squared plus 1 is just a 2x. So writing this a little bit nicer, what we have here is we've got a -1, let's see, times a 2x, which will give us -2x. And then if we drop that negative exponent back down to the denominator, that -2, what'll happen is it will turn into, let's see, an x squared plus 1 squared on the denominator. Now let's draw a number line like we would in calculus courses. So in calc, we would have made a number line that starts, they were worried about 1 to infinity. And we'd want to see, first of all, are there any values where f prime equals 0 or is undefined? And note is that our derivative f prime is not 0 or undefined. On the interval 1 to infinity, this means there are no critical values. So there are no critical values. In our interval.